Right, so we're recording. All right, so welcome to the BSI. This is the BSI Subspace Virtual Talks, co-sponsored by the Center for Translational Research in Neuroimaging and Data Science, TRENDS, and the IEEE Signal Processing Society. I'm Roger Silva, a research scientist here at TRENDS, and today it is my privilege to introduce our speaker, Dr. Daniela Hatt. She received her PhD in electrical engineering from Tel Aviv University, Israel in 2013. Dr. Lahat is currently adjunct assistant professor in the Department of Computer Science and Electrical Engineering at the UMBC and a researcher in the School of Electrical Engineering at Tel Aviv University. She held a postdoctoral research position with the Grenoble Images Speech Signal and Control Laboratory in Grenoble, France, from 2013 to 2018, and also with the CNRS and IRIT in Toulouse, France, from 2018 to 2020. Her research interests include tensor methods for machine learning, data fusion, and data analysis, as well as statistical signal processing. Dr. Lahat is a brilliant researcher whom I admire very much. I've followed many of her exciting research contributions since her early works on multidimensional ICA. She has since branched out into multimodal fusion, the development of joint independent subspace analysis, and more recently, its connections with tensorial decompositions. The exceptional quality of Dr. Lahat's work is noticeable in all her publications, and we are surely in for a treat. Today, she will be presenting beyond independent component analysis, subspace, coupled, and block decompositions. Dr. Lahat, thank you so much for being here and sharing your time with us today. You have the floor.
Do you hear me? Thank you, Rogers.
Yes, I hear you.
The very kind introduction. And I would like to thank all the people who attended this presentation, this talk. I'm just going to turn my video off for the talk. Okay, so in this talk, I'm going to speak about some models that extend the basic independent component analysis model into subspace, coupled, and block decompositions. Okay. And this is joint work with a number of people: Christian Jutin, Tulay Adeli, Jean-François Cardozo, Chagit Messer, and Helen Shapiro. So in this talk, I will start by presenting some background and preliminary material about independent component analysis. And then I will explain how this model extends to independent subspace analysis, and then to joint independent subspace analysis. The general setting which motivates this work is a setting that is common in many applications where we have a number of sources, which are here depicted by the musical notes, and a number of sensors spread in some probably unknown locations or locations that we cannot change or determine. And these sensors here are depicted using the microphone icons. And in this talk, we focus on the simplest linear model in which we assume that there is a single scalar coefficient. Here we denote it IR, where I is the index of the sensor and R is the index of the source. And this coefficient represents the overall channel effects between the signal emitted by the source R and the sensor I. And in most real-life settings, the locations or the coordinates of the sources and the sensors with respect to each other are in general not known. This is sometimes called a blind setting, or a setting that leads to blind separation methods. And the goal that will lead us in this talk is we would like to extract or to estimate or separate the source signals from their observations using the sensor data. So this is a very general setting that appeals in many applications. So we can start with a very simple model for the data. We can collect all the signals emitted by each source into one column of a matrix that we denote this matrix B. So the BR column collects all the signals emitted by source indexed by R. And the model for the observations using our simple linear assumption is that the observations are a weighted sum of the, at each sensor, they are weighted sum of all the source signals at each sample index, which in this talk will be the index J. And we can collect all the observations. For example, the observation Xij of sensor I and the source J into the matrix X, whose size is I by J, where the J indicates the sample index. So assuming that we have R sources, this observation model can be stated as a simple matrix factorization model where the matrix X is approximated as a sum of R rank 1 terms. So in this context, the matrices A and B are called the factor matrices or simply factors. And they are partitioned column-wise into columns that represent or associated with each of the sources. And mathematically, we can write this as a sum of the matrix X is a sum of R terms, for example, A1, B1 transpose, and so forth. So this is a very simple model to write. But the problem is that this model is not so simple to analyze. And the reason is that this matrix factorization is in general not unique as soon as we have two or more sources or signals to separate. And this non-uniqueness arises from the fact that we can always write choose an arbitrary matrix Z and insert it and have a different decomposition Z inverse and Z B transpose, which means that we can write the matrix X as a sum of R rank 1 terms, which can be completely different from each other. So they do not represent any real physical phenomenon. So the reason that we need a unique decomposition and so many models are aimed at achieving this uniqueness is that this uniqueness is necessary to achieve interpretability of the output, to attach a physical meaning to the output of the algorithm. So how can we achieve a unique factorization? We need something that is called diversity, which is the key to identifiability. We can define diversity as any constraint or assumption on the underlying factors or variables that generate the signals that help achieve uniqueness. And this type of diversity can take different types of forms. It can be assumptions of orthogonality or van der Monde or Toplitz's structure on the matrices. We can assume sparsity, we can assume non-negativity, or we can assume statistical independence, where in statistical independence, we mean that each column of the matrix B or each signal emitted by each sensor is statistically independent, is a statistically independent random process that is statistically independent of the other emissions of the other signals. So how can this assumption help us achieve a unique factorization? This is an approach that is known as independent component analysis, which means that we would like to write the matrix factorization as a sum of independent components. And the notations that we use is, again, the columns of the matrix B are a number of realizations of a number process, of a random process, for example, S indexed by R at all sample indices J, and these random processes are statistically independent, mutually statistically independent, so that the observation model can be written in the more classical independent component analysis notation in multiplicative form, mixing matrix A times the source vector S at each sample index, which is a sum of statistically independent terms or realizations of a statistically independent random process. So we can store these random vectors or their realizations as the columns of the observation matrix X, and at each sample index, there are also the sources, the latent sources that we would like to find out are the columns of the matrix B transpose. And the goal of this independent component analysis approach is to recover or estimate or separate the sources given the observations stored in the matrix X and the mixing model, the ICA observation model, and the statistical assumptions of dependence and independence up to arbitrary scaling and ordering, which are unavoidable ambiguities of this model. So in this talk, we focus on models that extend this basic independent component analysis approach. And we shall explain what these subspace or block decompositions are in this extension. And we shall briefly explain how they are related to concepts of data fusion. And we shall also briefly touch some links of these models to tensor decompositions. So the outline of this talk is that, okay, we presented ICA, where ICA is a single mixture of scalar or one-dimensional sources. The first extension is called independent subspace analysis, where we still have one mixture, but now the sources are multidimensional. And the second extension is that we have joint independent subspace analysis, in which we have several mixtures of multidimensional sources. That is, several mixtures of ISA, independent subspace analysis, analyzed together. So we begin with independent subspace analysis. We now modify the matrix factorization model. Instead of writing it as a sum of rank 1 terms, we write it as a sum of terms whose rank can be larger than 1. We call these ranks L1, L2, and so forth to LR, and they can be different for each source or for each low rank term. This rank can be 1, but it can be larger. And for this reason, the mixing matrix and the matrix B that collects these terms for each source is now block partitioned vertically. And the size of each block is the number, for A, the blocks are the size, the number of sensors times the dimension of each source. And the matrix B has the dimension of the number of samples times the dimension of each source. And for the same reasons that ICA, or matrix factorization, is not unique for 2 or more sources, also this factorization is generally not unique as soon as we have 2 or more terms. In this case, we would like to find a decomposition up to what we call essential uniqueness. It is not simply scaling, but we have a more elaborate form of scaling, which is up to arbitrary non-singular matrix ZR that can be different for each low-rank term. And of course, we have arbitrary ordering because whatever order we choose for the terms in the sum, we obtain the same observation matrix. So these are now our trivial ambiguities. And this essential uniqueness means that now we can identify only the span, assuming essential uniqueness, we can identify only the span of the columns of each block AR of the mixing matrix. That is only the subspace, which can be of dimension larger than 1, where the source signal lives. So what is the motivation for this extension of ICA? Where do we find multidimensional components that may be candidates for this model? In fact, multidimensional components may occur due to various complex relations and processes within the underlying phenomena that generate the data. And there are numerous examples. One application, which was the first application to demonstrate this model, is the extraction of a fetal electrogram electrocardiogram from measurements on the belly of a pregnant woman. So the idea is to separate the cardiac activity of the fetus from the mother, and it was shown that the best decomposition was achieved if the cardiac activity of the mother was modeled by a three-dimensional model, not a one-dimensional model. And this provided a better separation of the fetal signal. And it applies also in astrophysical processes. For example, when you would like to separate radiations from outside our planet or our solar system, for example, we can model it turns out that modeling the galactic emission, the emission from all the stars in our galaxy, from the cosmic microwave background radiation, which is a different process in the universe that emits radiation, then it is better to use a multi-dimensional model for the galactic emission to enhance the separation of the cosmic microwave background radiation. And other applications include studying neurological activity that is observed by a functional MRI or EEG. And a different type of multidimensional component occurs in convolutive mixtures, in which the subspaces may represent channel effects, not the original signals, but some other effects that happen to the signals when they reach the sensors. And in audio and speech enhancement, the subspaces can be used to model separate conversations, that is to separate disjoint groups of speakers. Sometimes we would like to separate individual speakers, but sometimes it is necessary or useful to separate groups. And another example is natural images where features can be sometimes represented using multidimensional elements. One of the questions that come up naturally is why not to treat the multidimensional components as a collection of one-dimensional components? Isn't it simpler? So there are several reasons, and some of these reasons are that if we use a true multidimensional or true subspace approach to such data, then we obtain higher accuracy in the reconstruction of the desired sources. We can have enhanced interpretability, as in the example of the fetal and maternal ECG. And there are also computational advantages because subspace methods, they separate subspaces. And the one-dimensional methods, they try to separate the subspaces into smaller elements. But since these subspaces are not separable, these algorithms can do needless work and just work too hard without any success. So another question is from the mathematical perspective, do these low-rank terms actually exist? Why don't we just write each of these terms as a sum of rank 1 terms? Why don't we go back to the basic model? So for this, indeed, for each model, when a term whose rank is larger than 1, for example, 2 or more, if this term indeed can be factorized using the model or the algorithm into several terms of smaller rank, we say that this term is reducible. Otherwise, this term is said to be irreducible. So, of course, we are interested in having irreducible low-rank terms in our model. And reducible terms, if terms are reducible but we do not pay attention to this, then this can cause problems such as non-uniqueness and non-identifiability in the output. And another point that is critical to understand is that the existence of these low rank terms of rank 2 or larger depends on several factors, but one of them is, of course, the data. But the other one is the model. And we shall now explain what we mean by the model. So we begin by a specific model, which is called independent subspace analysis, that generalizes ICA, where it assumes that the low-dimensional elements are realizations of independent multivariate, not stationary random processes. That is, this independent subspace analysis model, it relaxes the independence, the assumption of independence within each source vector in ICA. Sorry. And this means that each source vector at each sample index is now partitioned not into our independent terms, sorry, but into a smaller number of terms that are now vectors that are mutually independent, but within each vector, the random variables are dependent. Sorry. And again, we have the column block columns of the matrix B. They collect the realizations of these source signals for each source. So this is the basic independent subspace analysis model. So how do we construct a model with irreducible low-rank terms? Let us start with the simplest statistical model, which uses second-order statistics. And we are also interested in seeing if we can extend the joint diagonalization approach, which is common in independent component analysis, as we shall show soon. So first of all, we keep in mind the fact that two covariance matrices, one of which is non-singular, these two matrices can always be exactly jointly diagonalized, for example, by the generalized eigenvalue decomposition. So it means that we probably need more than two matrices or more than two types of diversity to construct these blocks. So in this case, we assume that we can use diversity among the samples within each source. For example, we can assume that or exploit non-stationarity and statistical assumptions to construct a model with these irreducible low rank terms. So what do? We assume that we have a partition of the samples. The index J is partitioned into a smaller number of, that we call it Q, of non-overlapping intervals. And we assume that in each interval, within each interval, the samples are have a different type of statistics. So the simplest assumption is that each source in this case is a zero mean, multivariate Gaussian, non-stationary or piecewise stationary random process with independent or decorrelated, because second order statistics is about the correlation, with independent samples. What does this mean in practice? It means that we can compute the instantaneous cross correlation between the signals emitted by each source, the mutual correlation at each sample index. And this cross correlation, which is now a matrix of size, for the size is the dimension of one source times the dimension of the other source. And this cross correlation, if we take the autocorrelation of the source with itself, then it's a matrix. For simplicity, we assume that it's non-singular. It is non-singular, sorry. And in the other cases, this cross correlation between two different sources is zero by the assumption of independence. And if we collect these covariance matrices, or if we compute the covariance matrix of the source vectors at each sample index for each time domain or frequency bin or whatever partition of the sample index, then we obtain that a set of covariance matrices that have a block structure, where the elements on the main diagonal are the correlations of the source with itself at each interval, and the zeros mean that different sources are uncorrelated, the same as in ICA. And this means that we can store these covariance matrices, the block diagonal matrices, in the Q domains in a structure, in a three-dimensional structure that we sometimes refer to as a tensor. So in fact, we obtain a tensor with frontal slices that are block diagonal. And these diagonal elements are in general different for each matrix slice, for each frontal slice. And similarly, we do the same operation for the covariance matrices of the observations at each interval q. These observations satisfy a linear model. So each correlation of the observations is the mixing matrix A times the block diagonal cross correlation, A transpose. It can also be written as a sum of R low rank terms. And we stack again these covariance matrices in a tensor whose size is the observations have the size of sensors by the number of intervals. So we fill this tensor again, and we obtain a problem that now we would like to estimate the mixing matrix using a model match between the tensor of the observations, which is given, and the model, which is the mixing matrix and a block diagonal tensor. And we see that also here, the statistical dependence and independence assumptions of independent subspace analysis have been restated as a deterministic model fit problem. So how do we address this problem, this model fit problem? How do we find the matrix A? So one way to do this is in the case that the mixing matrix is non-singular, it is invertible, then we can change sides and we can multiply the matrix of covariances of the observation, each covariance matrix of the observations on the left and on the right with the inverse of the mixing matrix, where the idea is that we now expect to reveal the block diagonal structure of each matrix slice. So this procedure is called joint block diagonalization. And as we mentioned before, in fact, if we take only two matrix slices, then we can always find an exact diagonal structure, not block diagonal, but always exactly diagonal structure using, for example, generalized eigenvalue decomposition. And only starting from at least 3 matrix slices or 3 intervals, the model is in general irreducible. If we enter 3 matrix slices that are block diagonal, in general, except for very special cases, we can keep the block structure also after this joint block diagonalization. So one message from this is that if we do something which can be regarded as a simplified data fusion, because this model can be regarded as a simple data fusion. We have 3 matrix problems. We have Q matrix problems, one for each interval. The common parts are the mixing matrix, which is shared for all these problems, but the observations and the latent block structure is different for each diagonalization problem. So we do a joint diagonalization or a fusion of 3 different problems. We solve them together using the fact that the mixing matrix is the same, and this allows more elaborate structures to be manifested in the data. And this also shows us that the existence of the blocks or the subspaces depends on the model, because if we choose a model with too few matrices to block diagonalize, then these blocks will not appear in the model. The next point that we discuss is the uniqueness of this joint block decomposition or of this tensor model match. So of course we need at least 3 matrix slices, and it can be shown that this model is essentially unique, which means that we can identify the mixing matrices A up to the scaling by an arbitrary mixing matrix and ordering of the R terms. This JBD if the matrix slices are all non-singular covariance matrices or have this property, the only case, if and only if, the only case that this decomposition is not unique is only if there exists a pair of sources and there exists a non-singular matrix that satisfy this relation. Now, in order to understand what this relation means, We can look at this diagram. It in fact says that if we look in the third dimension at the autocovariances of the sources across all the intervals of one source and all the block covariances of a different source in all the intervals, only if all these two sequences of matrices, they satisfy this certain equivalence relation for all these intervals, then we have non-uniqueness. And this is, in fact, a generalization of a result that is known for joint diagonalization. In joint diagonalization, these matrices are not block diagonal, but diagonal. And we have something that is called sometimes a spectral diversity or variance diversity. We know that the joint diagonalization problem is not identifiable if we have two spectral profiles or two variance profiles that are proportional. And in fact, this result is a generalization, or in the joint diagonalization case, it is a result that is known for a longer time in tensor decompositions. There is something that is called the Kruskal rank, which is in fact equivalent to the fact that in the scalar case, if these two vectors are proportional, then the block or the joint diagonalization is not unique. So this result, which we show here for the block case, is a certain type of generalization of this result of Kruskal for tensors that have a latent block decomposition. And of course, once we estimate the matrix A, then if it is unique, then we can separate the sources by just using the inverse. Another point that I wanted to note here is that this non-uniqueness, this condition of non-uniqueness can hold only for the case that two sources have the same dimension. Or in other words, if two sources in the block structure have different dimensions, then there is no risk of non-uniqueness, where non-uniqueness means that we have some confusion between the elements of the sources and we do not separate them properly. So this result tells us mathematically that if we have a decomposition of sources of different dimensions, then the sources of different dimensions cannot mix with each other, and we cannot have a result of a block diagonalization or a separation using this model, but the sources are not separated. Because we have to remember that jointly diagonalizing matrices is one thing, but separating sources is another. So non-uniqueness means that we obtain a nice diagonal or block diagonal structure, but the matrix A is not unique. It does not separate the sources. So we now see that if we have sources of different dimensions, the risk of having this non-uniqueness or non-identifiability problem is smaller. And this means that the block size or the subspace dimension can be regarded as a type of diversity. In fact, it enhances the uniqueness of the model. So to conclude about independent subspace analysis, we have shown that independent subspace analysis inherits from the independent component analysis the inability to separate sources that are Gaussian and identically and independently distributed. And if we want to bring about the block structure in the model that we presented, we need an additional type of diversity beyond ICA, such as non-stationarity or sample dependence that allows us to build this joint block decomposition. Sorry. In this case, we really have, in general, irreducible blocks as soon as we have a fusion of three slices. And we have also shown that the independent subspace analysis is associated with tensor block decompositions. So the next step, sorry, is the joint independent subspace analysis model. And in this case, we have now a collection of decompositions. we have a collection of k data sets where each data set individually can be separated, can be expressed as a matrix factorization problem with its own matrix. For example, the first data set is the product of the matrix A1 times the matrix B1 transpose. We assume that all these decompositions have the same number of sources R, but in this case, each decomposition has its own variables. And due to the block assumption, again, each mixing matrix is partitioned column-wise into blocks. The matrix A has the blocks, a block partition, and same for the matrix B. So far, nothing has changed, but we can link these data sets in order to enhance the decomposition if there is indeed a link between these data sets. And one option to do so is by first assuming within each decomposition the same assumption of independent subspace analysis. For example, the matrix factorization X1 is still an ordinary independent subspace analysis problem, and the same for the K problem. They are still in legal and normal independent subspace analysis problems, but now we have an additional assumption that all the sources, for example, all the sources indexed by 1 are statistically dependent. They are not the same, but they contain samples generated by statistically dependent random processes, and the same for the other sources. So we have independency within each mixture between the sources, but across mixtures, we have dependency between sources. One implication of this link between sources is that the uniqueness problem is now alleviated. We still have the same uniqueness of each, the scaling is still up to an arbitrary matrix ZR, which can be different for each data set. But now the permutation problem, the arbitrary permutation, is still arbitrary, but it is the same for all the data sets. So now the permutation ambiguity or permutation uncertainty is a global permutation. And this turns out to be helpful in various data fusion applications. In the special case that all these blocks have size 1, which is a simpler model, we don't have multidimensional blocks, but in fact, each problem is just independent component analysis. Then this model is known as independent vector analysis. And both joint ISA and IVA, which is the special case of rank 1 terms, they use what we call soft links among the data sets, which means that we assume dependence, statistical dependence across the data sets, but still each data set has its own mixing matrix, which can be different in general, and the samples themselves can be different. And this model is sometimes referred to as the joint independent subspace analysis model. In order to further see the link to independent subspace analysis, we can also write this problem in terms of random vectors, where for a fixed index k of the data set, we still have an ordinary independent subspace analysis problem with independent random vectors, but across mixtures, these random vectors are statistically dependent. And within one single vector, within which single ISA problem, we still have the usual ISA model that the source vector consists of statistically independent vectors and not scalars. So why are we interested in this joint ISA model that subsumes both independent subspace analysis and independent vector analysis? It subsumes within it the independent component analysis, which is a successful data analysis method on one hand, and on the other hand, the independent vector analysis emerges as a flexible method for data fusion, for multi-set data analysis, and more. So we have both benefits of these two models in the joint framework. Another benefit is that using the soft links or the statistical links, it allows each dataset or mixture to keep its own individual variables and parameters, which is opposed to other data fusion models that use hard links in which the parameters, for example, the mixing matrix or the source samples, are identical across datasets. So this model allows more freedom within the datasets that we are analyzing together. And for this reason, the joint ISA is a good candidate for the fusion of heterogeneous datasets. So in order to see the motivation for joint ISA, we can go back to the motivation for independent vector analysis, where we see that these applications are potentially useful also for the joint ISA framework. So IVA was first of all proposed not for data fusion, but for solving the frequency domain blind convolution problem that we have in audio signals. And the authors wanted to solve the convolutive mixture in time to convert it to the frequency domain where it becomes a multiplicative problem at each frequency bin. But the problem is that when you transform this convolutive mixture to the frequency domain, you have multiple instantaneous ICA problems. And solving each ICA problem has its own arbitrary permutation. And so we cannot reconstruct reliably a signal if within each frequency we have a completely different separation of the elements of the same signal. So they propose to use independent vector analysis and the dependence as some sort of model of latent dependence within each source across frequencies to fix this arbitrary permutation to a global permutation that allows the extractions of the sources in a reliable manner. And other applications that have been proposed for the independent vector analysis model are the multi-subject study of brain activity using functional magnetic resonance imaging, fMRI, where each data set is the recordings from a different person or subject. It can also study dynamic changes in brain connectivity, where the dynamics are represented by different mixtures. Another application that was proposed in hyperscanning, which is the study of the EEG activity of two people who are interacting with each other. And a different application is the multi-camera data fusion with the purpose of detecting an abandoned object in a series of video images. So we see that also even the basic IVA model is very flexible and can be applied to different settings. So the joint ISA, it combines both the data fusion power of IVA and the flexibility of independent subspace analysis in further representing different types of latent phenomena. So now we present a more specific example that shows that joint ISA can achieve uniqueness when ISA falls short. That is, we show now a case that is not identifiable using ISA, but the joint ISA can provide the uniqueness. And this will also serve us to show an analog of the joint block decomposition or the joint block diagonalization problem of a single mixture. And we shall show that it can be analogous to a more elaborate decomposition, which is a coupled block decomposition of a number of matrices that is associated with the joint model. So to show this result, we use the simplest or probably the simplest joint ISA model, in which we assume that each source is a Gaussian multivariate of some dimension that may in general be different for each data set. And the samples are independent and identically distributed in this random process. So this is a setting that is impossible to separate using ICA or ISA. And we also assume for simplicity that the mixing matrix of each dataset is invertible. And for this reason, all the uniqueness, identifiability, and irreducibility results that we shall show now in this model are only due to the link among the datasets, because each dataset by itself is not identifiable and not unique. So to compute this model, we go again to models based on second-order statistics. And similarly to the non-stationary problem of ISA that has led to joint block diagonalization, we compute now the cross-correlation between two signal elements, but in all the combinations of different datasets. So we compute all these instantaneous cross-correlations. And for the same source, we assume that these cross-correlations, we have statistical dependence, so this cross-correlation is a non-singular matrix if we compute the cross-correlation of a source in dataset, one dataset and the other, but cross-correlations of different sources, either within or in different datasets, they are always zero by the assumption of independence. So if we stack all these cross-correlation elements for the sources to compute the cross-correlation across all the sources in all the datasets, again, we obtain for each pair of datasets, we obtain a cross-correlation matrix that is block diagonal, where the diagonal blocks reflect the autocorrelation of a source with itself, and the off-diagonal terms are zero because we have statistical independence between different sources. So again, we have a set of block diagonal matrices, and again, we have shown that the statistical assumptions of independence have been restated as a deterministic structural constraint. We do the same computation for the cross-correlation of the observations, because the observations are what we have in hand. This is what we measure or see. So due to the linearity of the model, these cross-correlations of the sources across all data sets are, again, have a structure. They are the product of mixing matrix for one data set times the block diagonal cross-correlation matrix and the mixing matrix of a different data set. So if we try to estimate all the mixing matrices simultaneously from all these matrices, we obtain a decomposition that we call it a coupled block decomposition. And similarly to the joint block diagonalization scenario, if the mixing matrix is non-singular, we can change sides and obtain a coupled block diagonalization, where the purpose is to find matrices A, K, A, L, and so forth, all the mixing matrices, such that if we apply them to the observed cross-covariance matrices, we obtain a diagonal structure. And the assumption is that if this model can be shown to be unique, then this procedure, if we reveal the block diagonal structure, then we have a unique estimate of all the mixing matrices in all the data sets. So what does this coupled block diagonalization model look like? This illustration shows a model of K data sets, where on the right we see the block diagonal structure of the cross-correlation matrices across data sets. Here we have, in this example, we have 3 lower terms. So we have 3 blocks for each data set. And here, the dimensions, for simplicity, the dimensions of the sources of the first source in all data set is 2. The second source has dimension 1, so it has a smaller block. And the third source has dimension 3, so it has a larger block in all the data sets. So graphically, the purpose is to apply all the combinations of all the inverses of all the estimates of the mixing matrices to the cross correlations and to obtain this block diagonal, to reveal this block diagonal structure. So again, we have this basic question: do the blocks exist? What makes this model block diagonal and not further block diagonalized. So we have the same concept of reducibility or irreducibility. If indeed the model is such that the blocks cannot be further be reduced by any transformation on the observations, then the model is irreducible, otherwise it is reducible. And it can be shown mathematically that in the case of two data sets, this problem can be expressed as joint eigenvalue decomposition. And therefore, for two data sets, we can always have an exact diagonalization. So we cannot reveal any block structure in two data sets. But as soon as we have three data sets or more, the blocks are in general irreducible. And this is another mathematical evidence that the fusion of at least three data sets is necessary for the existence of the block structure or of the subspaces, subspace model. So the next question, after showing that the blocks can indeed exist, we discuss the question, when is this model identifiable or unique? When does it produce amazing? Sorry, when does it produce a set of mixing matrices that can really separate the multidimensional sources in all the data sets? So we show here an example again with the same three sources. And for simplicity, we assume that indeed these blocks are not only irreducible, but within each block, we do not have zero values because zero values make this the computation more complicated. So here we show the simplest case. So the result says that, sorry, that this coupled block diagonalization is not unique only if and only if there exists at least one pair of sources that for all data sets, they satisfy a certain equivalence relation with a set of k non-singular matrices, where the k is the number of data sets. So to see what this equation means, we can collect, for example, for the first source, all the diagonal blocks in all the cross correlations of source number one, and we collect them in a single matrix in the same order. And we do the same for a different source. For example, for the third source, we collect all the blocks in the same order and place them in a different matrix. So non-uniqueness exists only if we can find a block diagonal matrix with non-singular block diagonal elements that satisfies this relationship among the two matrices that collect all the cross correlations of all the sources. And similarly to the JBD identifiability that we have shown previously, also this non-identifiability condition can hold only for sources that have the same size. So if sources have or blocks have different sizes, they do not cause non-identifiability. So also here we see that in this joint ISA model, if we have a diversity in the sizes of the sources or in the sizes of the blocks of the subspaces of the sources, then we can alleviate the problem of non-uniqueness. And to remember what we had with the identifiability of joint block diagonalization, there we had a sequence of block matrices corresponding with one source and the block matrices corresponding with the other source. And we wanted them to be non-proportional in a certain sense or non-equivalent. And here this equivalent relation is more elaborate because it requires different types of a set of matrices to generate this connection. So in a sense, we can say that this a coupled block decomposition is a variation of joint block diagonalization, but in this case, this model cannot be stored in a single tensor. So again, since we showed a relationship of the uniqueness results of JBD to the Kruskal condition of no two proportional columns. This can be regarded as another variation of the Kruskal condition, but to this coupled block decomposition. And when the diagonal blocks do contain zeros, uniqueness is still possible, but the conditions are more elaborate. And we also would like to remind that the uniqueness conditions of joint ISA, they extend known results, prior results on the uniqueness of IVA using second order statistics. And in particular, it has already been shown that IVA can also identify a Gaussian independent and identically distributed sources, a case that is a lost case for ICA and ISA. So just to conclude, we have shown a joint ISA with a single type of diversity, which is the multiset diversity. But of course, this model, like the underlying models that it subsumes, it can combine several types of diversity. It is very rich. And similarly to IVA, we can exploit not only the multiset diversity, but also non-stationarity within or sample diversity within each source, which leads to a coupled for tensor decomposition. And for the joint ISA, also we can use non-stationarity or other sample diversity. And in this case, this third dimension contains blocks, not just vectors, where again, each frontal slice is a block diagonal or diagonal matrix. So for each frontal slice, we have the same coupled block decomposition, but here we also have a third dimension. So to see where the third dimension comes from, we can also look explicitly at the generative model. Each cross correlation of the sources across data sets and, for example, at each in time interval can be written using the same model. So we have these matrices A, K, and AL. Sorry, this should be a transpose on two sides. And now the Q, or the what is written here as T, is the third dimension. So we have really a coupled tensor block decomposition to further enhance the uniqueness of this decomposition. And further enhance means that this model can also uniquely find matrices A that are not invertible, and even if they are, we have more sources than sensors, which is the underdetermined case. So to conclude this talk, we have shown that the existence of block or subspace structures depends. Sorry, it depends. Sorry. Yep. So we have shown that the existence of the blocks or the subspace structure depends not only on the data itself, but also on the model. Because if we have an inappropriate model, we will not have blocks. And we have seen that the presence of blocks or subspaces of different sizes can enhance desired properties such as uniqueness and identifiability. And we have also shown that coupled or joint decompositions of multiple data sets or of matrices can further enhance uniqueness and identifiability. And in general, we show that the joint ISA is a flexible framework that combines both advantages of ISA and IVA representing data, and it is also suitable for data fusion of heterogeneous data sets. Other points that we have not mentioned are, for example, that it can handle more elaborate cases where some sources are shared across data sets and some are not shared. And it can also handle underdetermined the less sensors than sources setting. And of course, it is not limited to second order statistics because we can apply any methods such as those developed for ICA to achieve this decomposition. And of course, we have not addressed many other important topics like optimization and how to find the sizes of the blocks. So these are all important questions, but outside the scope of this talk. So this concludes my talk, and I would like to thank you for your attendance and for your patience and listening.
All right, thank you so much. That was an amazing talk. Thank you, thank you. So I have here on chat quite a few questions coming in. So I'm gonna start with one that came in early about ISA. Where is it? Here. So the question is, how crucial is the assumption of non-stationarity for independent subspace analysis?
It is not crucial at all, but it is one way to construct the blocks. You can have ISA with, you don't need it, but it is just one of the many ways to have diversity. The same as with ICA. You can do ICA with no stationarity, but you can also do it with stationary sources that have sample dependence, that have colored spectra, or using other types of higher order statistics and so forth.
All right. So this is basically getting to the point that you don't need, it's not sufficient to have only independence. You need something else. Stationarity is one of those things.
You need some diversity to make the blocks not be reducible, or the subspaces, to make them appear, in a sense, to make your model see the subspaces or the plots.
Mm-hmm. Thank you. So a follow-up to that question is also for ISA, independent subspace analysis. Can you please point out the relation or difference to canonical correlation analysis?
As far as I recall, the IVA model of two data sets is identical to the canonical correlation analysis model.
So it's a difference in the number of data sets that independent subspace analysis is only one data set, for only one data set.
If you use one data set, you have ICA or you have PCA or something like that. If you have IVA with two data sets, this is, as far as I recall, it's identical to CCA, which is also the reason why joint ISA in the block case that I showed for two data sets, it boils down to generalized eigenvalue decomposition and exact diagonalization. It's a result that has already been shown a long time ago for CCA.
Right. Awesome. So let's see. Have here quite a few questions that came in all together, so I'm going to just go one by one. Can you please give an example of an application where joint independent subspace analysis has advantages over joint independent component analysis or parallel independent component analysis?
I think perhaps you can give a better answer because I saw you have a recent paper using joint ISA.
So yes, so the idea is, I would say here is that with joint independent component analysis, you have that case where of hard linkage between the models. So it has a shared mixing matrix. In that sense, joint independent subspace analysis is more flexible, that it doesn't impose that restriction. But at the same time, if you're looking at heterogeneous data where you are not able to build soft linkages or estimate them, say you have data from electroencephalography and fMRI, then the time points and the spatial locations are just not corresponding. You can't estimate joint distribution between modalities directly. So you kind of, in that particular case, depending on the type of data, your hard linkages are the only thing you can extract. So what I'm trying to say is that it would not be possible to leverage these other types of diversity that joint ISA is able to leverage. And in regards to parallel ICA is ICAs running in parallel with an additional regularizer term that optimizes for correlation or similarity in the mixing coefficients. So in comparison to joint independent subspace analysis, I think you could think to some extent that the joint independent subspace analysis can match or is, it's as if you were running the parallel ICAs with an additional joint ICA cost between the columns of the mixing matrices. And we have published on a model that tries to exploit that directly with joint independent subspace analysis. Actually, was using independent vector analysis. And yeah, I can put in a reference here for later. But then if it's okay, I'm going to move on to the next question, which is,
thank you.
With the relaxed assumptions of independence, how does the interpretability change? With ICA, we can obtain subject-level features that may be used in further downstream analysis, such as classification or the incorporation of covariates. Does joint independent subspace analysis offer the same extension? And by extension, I think she means utility.
Yeah, so yeah, of course, this is a very good and important question. So the reason that these models were proposed in the first place was indeed to improve the interpretability and the separation quality. For example, either in the fetal and maternal ECG problem, if you use separation to one, of course, if you model a source that is, say, again, the dimension that, or the subspace is a property, like I said, of the model and of the data. And once you have certain data and certain model, then the subspaces are either there or they are not. But if they are there, it is better to treat them and not say to respect their subspace and not to try to factorize it. On one hand, the factorization does not always have a meaning. For example, in the cosmic observations case, you separate, for example, the galactic observations from the cosmic microwave background radiation. The galactic component is multidimensional. I think it has 4 dimensions in the ICA, but the decomposition is done by a linear method, but of course you can later use other types of processing, for example, to study only the galactic component. So it is the same thing as in ICA, you can do some, or IFA, you can do some, or sometimes you need to do some post-processing. So this model, of course, does not do everything, but it can serve as a good separation part in the separation step in the pipeline of processing your data.
Yeah, I've tried to make that point before, that by not imposing independence within the subspace, you have flexibility to do other kinds of decompositions down the road, and you potentially have better representation of complex features.
You can assume, for example, that you have nonlinear mixtures. So nonlinear mixtures, maybe they are linearly mixed. For example, groups of speakers, they are speaking together. There is too much reverberation or correlation in their speeches. So you can separate the groups of speakers if they are standing in different groups. But later you can process the speech using other methods that are suitable for each group separately. But it still simplifies your original separation problem.
I agree with that. That's a good example.
It reduces the dimension of the separation from a big separation problem to small groups that you can handle separately. for example.
That's a very good point. So another one here is what optimization techniques are used? And I think you kind of hinted at that. With FastICA and Infomax approaches, we use different estimates of non-Gaussianity for optimization, which requires different optimization constraints. What is the parallel implementation with joint independent subspace analysis?
Of course, this is a critical question, a very important topic. So I think in some sense, this very similar to ICA, there are basically two, say, communities of models, and therefore two different types of algorithms. One is based on tensor or matrix decompositions, which usually are some model fit or optimization methods for model fit developed in the tensor or matrix decomposition community. And the other one is based, I think perhaps, again, you are probably more familiar with this type of methods that are using the a certain distribution model, and then you are trying to minimize some criterion like, I don't know, to minimize the mutual information or something like that. I'm not so familiar with this, but there are plenty of optimization methods. But on the other hand, joint ISA, I think there are less applications, which is also why I would like very much to promote it in this talk. So I think there are fewer algorithms, and I think they are mostly either based on algorithms that are more general for coupled block decompositions, coupled tensor decompositions. And then there are the models that are, I think, that you are working on them more using other types of non-Gaussian distributions.
Mm-hmm. But I think the question, I don't know if it was clear. The question is, which of those two did you choose for joint independent subspace analysis, your implementation? Are you using?
My implementation was based on my personal implementation was based on minimizing the max. When you have a statistical model that is simple and tractable enough, you can write the maximum likelihood solution and obtain a closed form expression from which you can derive a nice expression for the gradient, for the Hessian, and you can derive gradient or Newton type algorithms, for example.
Mm-hmm.
But there are all the optimization methods are. I mean, there are so many optimization methods.
Right. Yeah.
It also depends if some methods are based on finding whitening and orthogonal, finding the orthogonal unmixing matrix or just the unmixing matrix. Some of them do not assume invertibility. So I think it really depends. I do not have a specific optimization method to recommend. I think
right. Yes.
there is a big variety of methods.
I see.
But of course, also when you work with several data sets, you have more data. You need more efficient, I think this is an important point, you need more efficient computational methods, because if you have more data sets, you can have larger data. It's difficult to compute using methods that are adapted for small or single data sets.
Right, yes. Especially, if the number of data sets grows quickly,
yes,
beyond like 20 or 50, then you can see a really big slowdown on the computations. So definitely, yeah, that's an important question to address. So in the interest of time, I'm gonna end the recording. There is one more question that I will copy into the Slack channel, and then we can address offline.
okay.
We can stay here maybe another 5 minutes and discuss it outside of the recording, just for whoever wants to get the information right away. But then later we'll address it again on Slack so everyone can have access to it. Just don't want the recording to get too long. Okay, I'm gonna wrap up the session and again thank Dr. Lahat for this great talk. I think I got a lot of positive feedback from it on chat, and thank you everyone for attending today. And like I said, we're gonna continue here and on Slack later on. And thank you so much for everyone to come. I'm gonna stop the recording now.